So we looked at general uh, matrix equations to give us a sense of what linear operations are and what they could be used for, and getting unique solutions and seeing the span of a vector space. Now we're going to focus on function space, because solutions to differential equations are functions. Okay. Definition: a linear operator on a function space is one where the linear operator operating on a sum of two functions is equal to the linear operator operating on one function plus the other. Okay, and we could say this succinctly as the linear operation commutes with sums. Okay, you could kind of say that in a modern mathematical language that way. Okay, so the operation on the sum is the sum of the operations. Okay. And the second condition is that a constant times a function with the linear operator acting on it is equal to that constant times the linear operator operating on the function. Or in other words, linear operations commute with scalar multiplication. Okay. So those are the two conditions of linear operators. You could write this kind of in one sentence by saying that for scalar multiples alpha and beta on the functions f and g, you get this relation, okay, which occurs if these two are true. Okay, and we're also going to, we're speaking about the language of linear operators. We could look at differential equations as, a subset of them as linear operators on functions, and one operator we need is this operation that takes a function and gives you its derivative. That will be the differential operator. Nothing deep here, okay, with the change of the symbols of now using d for dx and dn for dn dxn. Okay, this is just about the change in mindset, the shift in mindset. Okay, you're not thinking about the function as much as you're thinking about operating on that function. Okay. The nth order differential operator, the linear one, okay, that we'll be considering is this. This is linear. Okay, you can see that. Over here, okay, any operator that acts this way will be linear, because you could actually take a look at a function y and check the linearity, the two properties we have above. Okay, so this an x, an minus, these could be any functions of x. Okay, we're going to focus on a subset where an of x is never 0 on an interval, and these coefficients, all of them are continuous. Okay, but there goes the just in general that word. A homogeneous nth order linear differential equation has form that you see here, where the operator acting on y, so this should be a y there, okay, and you see you have y's everywhere in these derivatives. Okay, so this is just the extra thing that should have been there. But anyway, it's homogeneous because when this differential operator acts on y, you get 0. Okay, in some sense, you could kind of think about it as annihilating y. Okay, you take y, operate on it, and it gives you back 0. Okay, that's called homogeneous. Okay, and it's important to pay attention to that. Just it's not trivial. A non-homogeneous nth order linear differential equation has form that you see here, pretty much exactly as above, with this y also missing there. And you get that L acting on Y gives you g of x, okay? Where g of x is not identically 0. It could be 0 at a point, okay? We're actually going to consider, different functions. But yeah, so it's not identically 0, means it's not completely, it's not just 0 everywhere. That would be a homogeneous one, right? So if you have the situation where g of x is 0 on the entire interval you're considering, then that's just a homogeneous one. So it's just to differentiate between homogeneity and non-homogeneity. Linear independence. Okay, so we talked about that with the vectors above, but let's look at this in terms of functions. So a set of functions that you see there is said to be linearly dependent on an interval I if there exists constants C1 through Cn, not all 0, such that this equation is true for all x and I. What is that telling you? Okay, all that means is that you would be able to write one of these functions as constant multiples times the other ones. Okay, that's, that if not all of these are 0, then you could move some of them to the other side, and you'll be able to write one of the functions in terms of the constant multiples and sums of the other ones, and that's what we want to avoid if we're thinking about linear independence. Okay, so if the set of functions is not linearly dependent on the interval, it is said to be linearly independent. In other words, a set of functions is linearly independent if all these c's being 0 is the only solutions that satisfy the above equation. So if you want this to be true, and all of your functions f1 through f sub n are linearly independent, then the only way to make this true is to set all the c's equal to 0. Okay? And relying back on that discussion that we had with general vectors, okay, and you could think about functions as vectors, right? They're kind of vectors in this R to the R space. Okay, so they are vectors in a sense. So going back on that, linearly independent functions have different information in them. Okay, they're not just constant multiples of the other, right? So that's to give you a kind of sense, a mathematical intuition about in linear independence. In some sense, linearly independent functions point in different directions in function space. Okay? Just to rely on our previous intuition for the simpler case of R2 that we looked at. And looking at n equals 2 here, if this equation is if you have two functions that are linearly dependent, so there is so C1 or C2, one of those doesn't have to be 0 to make this true. Like, let's just, without loss of generality, take C1 to not equal 0. Then we could move C2 to the other side and divide by C1. And, here you'd have a negative there when you do that. But the important thing here is to notice then that in this case of n equals 2, this just means that when these functions are not, when they're linearly dependent or not linearly independent, then one function could be written as a constant multiple of the other. With greater than 2, you also get sums in there, but the general gist of a lack of additional information is there. Okay. So some examples to consider here. F of x, you have x squared in x times the absolute value of x. And don't forget that, x is equal to x when x is greater than or equal to 0, and negative x when x is strictly less than 0. Okay, that's the definition of the absolute. So in other words, you know, if we draw these out, we'll have this be x squared and we'll have that be x, absolute value of x, okay? So it's kind of, on the negative x-axis, it's the mirror reflection about the x-axis, okay? And on the positive x-axis, they're the same. So they're linearly dependent on from 0 to infinity. Not only is one a constant multiple of the other, they're actually equal if you consider just this interval 0 to infinity, but linearly independent on negative infinity to infinity, okay? And so any time you go to the left of 0, you're going to get linear independence. And so what does that mean? What is the key takeaway with that example? Is that linear dependence and independence depends on the interval you consider, okay? So that's important. You have to consider the interval. And we want to check, let's look at another example here with more than two functions. We want to check that these are linearly dependent. Okay, and here you could kind of play around and try to write one of them as constant multiples and sums of the others, okay? And it turns out if you do that, and you play around with it long enough, one combination you could end up with is that f2 of x, which is equal to square root of x, is equal to 1 times f1 of x, which is square root of x, plus 5 times f3 of x, which is x minus 1, plus 0, and 0 is a constant, so you could definitely use that, x squared. Notice that that's just 0, and you get, and this should be 5x, and you'll get square root of x plus 5x and minus 5, okay? I'm missing a 5 from in here, so this should be plus 5, okay? So you'll get a plus 5, these 5s cancel, all right? And you do indeed get that these relations are true, okay? So play around with that long enough and you could figure it out. Of course, that seems tedious, so we should develop a test to figure it out rather than just, hey, let me keep trying as many combinations as possible and spend so much time, right? So we want some tests to figure out linear independence of functions. And this is where the Wronskian is going to come to the rescue, unless you enjoy spending long hours figuring out linear independence of functions. So the Wronskian, suppose each of the functions f1, f2, fn of x possesses at least n minus 1 derivatives. The Wronskian of a function is this determinant, okay? So that's just the definition. Okay, you just take this n set of functions. You take all the derivatives up to n minus 1, and you know this is a square matrix. Okay, so note this is an n by n matrix. That could be a little confusing because you look and you see n minus 1 over there, but don't forget that this is kind of like saying this is the zeroth. The function here is the zeroth, so it's like 0 to n minus 1. There's n of them, okay? And so let's look at a particular Wronskian, okay? So if we have this function f1, of x equals x, f2 of x equals x squared. We calculate the Wronskian with the derivative of x is 1, the derivative of x squared is 2x. Take the determinant, which, you know, for 2 by 2 matrices is these multiplied together minus those multiplied together, and you get x squared. Okay? And so we're going to be using this Wronskian to check linear independence. So it's not, hopefully it's not a spoiler. So notice when checking linear independence, we're trying to solve this equation, okay? Now, you have, and you're solving this equation for two unknowns. What are the unknowns here? C1, C2. And this should now start reminding us about this idea that we were talking about when vectors span R2 before, okay? So you want to solve for a C1, C2. Two unknowns, one equation. Does it work? No, right? You need more information to isolate one of those degrees of freedom, okay, to kind of corner it. So what do we do to get more information? We take the derivative, okay? Now the derivative is not this just simple trivial kind of operation where you just taking, you know, this equation and multiplying it by a constant. Say that would be trivial, right? You're not changing any of the information. You're just kind of scaling that information. On the other hand, this has independent information in it, right? You're looking at slopes now. Before you were looking at the function, and now you're looking at how they change. So there's more information to it, okay? And so what we're trying to solve, so we take this derivative, right, of the first equation to get that additional piece of information. Now we say, okay, maybe we have, you know, enough information to solve for C1 and C2, okay? And that turns out to be a very important route to take, right? Because we have this theorem down here. This theorem tells us if these functions, this set of functions, are a set of differentiable functions whose Wronskian is non-zero at any point, then they are linearly independent, okay? And just to be clear here, this is differentiable up to n minus 1, all right? Maybe it should be emphasized. Okay, because you're going to take, for the Wronskian, you want n minus 1 derivatives up to n minus 1. Then they are linear. And notice this is a if-then statement. So if they are linearly independent, can we say that the Wronskian is non-zero? It turns out not to be the case for just general functions, but we do get this if and only if statement for solutions of differential equations, okay? But bear with me for a little bit, and let's just look at just general functions here. We're talking about functions, we're not talking about solutions yet. So we could ask this question: when are these two functions here, a and, you know, exponential with a and b constants, linearly independent? Well, let's use this theorem and check when the Wronskian is non-zero. So we take the Wronskian, right, by having the function and then looking at, so this right here is the derivative of that. This is the derivative of that. And when you take the determinant, you get this here. You get that this is not zero when a does not equal b. And so we're guaranteed that these two functions will be linearly independent by the theorem above, okay, when A does not equal B. We have that guarantee. Now, the only case that we're not looking at here is when A equals B. Are they, that's, if so this just guarantees us when they're not linearly independent. But there could be a case where they are linearly independent, but the Wronskian is non-zero, or the Wronskian is zero. Okay, so there could be that case, but it turns out that for this particular example, that would be when A equals B, but we could easily check when A equals B, this is exactly the same function, so clearly they are linearly dependent in that case. And so we do have, at least for this here, that they're linearly independent only when, if and only if this A does not equal B. And let's look at this remark over here. It should be not equal to 0, okay, to comply with the theorem. So linear independence is necessary but not sufficient for the Wronskian being non-zero, okay? All that means is that if the Wronskian is non-zero, then you're guaranteed. It's necessarily the case that that your two functions or your n functions are linearly independent, but your n functions linearly being independent does not guarantee that the Wronskian will be non-zero. And the quick example is these functions that we have here, x and x times absolute value of x, okay, which we looked at before. You take the Wronskian of these and you be careful with this absolute value in taking the derivative, okay? But if you do, you get this relation and it is 0. But they are linearly independent on R. They're not linearly independent on 0 to plus infinity, but they, in general, I mean, if you're going into the negative x-axis, they are linearly independent. So here we have a situation where Wronskian equals 0, but we get two linearly independent functions depending on the interval that we look at. We could look at R, okay? So it's necessary but not sufficient for the Wronskian. Linear independence is necessary but not sufficient for the Wronskian to be non-zero, okay? And again, we're primarily going to be concerned with not just arbitrary functions, but solutions. And when we look at solutions to linear differential equations, it turns out that we could get an if and only if statement. Okay, so you have sufficient and necessary. So to tie in this entire section and just in general on linear independence, we saw above with vector spaces that if we wanted to see whether two vectors whether they span a space, whether they're linearly independent, and that we could represent any vector, say x, as equal to C1 U plus C2 V, we ended up with this matrix equation. Where C1 and C2 are what we were solving for, and we had this x1 and x2 is for an arbitrary vector. And in general, we're going to get a unique solution. Okay, so these two vectors will be linearly independent, and we'll get a unique solution when the determinant okay, does not equal 0. Okay, you could invert the matrix. Well, that's incredibly reminiscent of the Wronskian. Okay, the Wronskian is the determinant of this matrix there. You could look at it in the case of the 2 by 2 functions, and you could draw the parallels here between this matrix here and that matrix up there. And you're basically asking if the only solution to this matrix equation, which notice here is this is trivial solution, right? So you're looking for what functions, what vectors will, when operating with this matrix on that vector, that you'll get 0, okay? So that's kind of sometimes called the null space, all right? And two functions are linearly independent when the only solution is just the vector 0, okay? When C1 equals C2 equals 0, you get linear independence. And we saw how we took, just to kind of motivate the Wronskian and why it works, is we get this second equation that gives us more information. So it's in a statement about the slopes, all right? And so just like the Wronskian, which is the determinant being not equal to 0, implies linear independence, we have the same thing going on here. When the determinant's not equal to 0, then the only solution for the 0 vector here will be that these vectors will be 0. So tying again all of that together and building that intuition on what linear independence means, I think is important, okay? Because it is kind of weird seeing a determinant here of this matrix, but hopefully now everything is clear and tied in together.